Hello, everybody. I'm Andrei. Everybody can hear me in the back? Yeah, cool. Don't be shy to shout if somehow I lose my voice or it doesn't reach you very well. So I'm glad to be presenting again at Hash Days. I was here last year and I enjoyed it. Today I'll be presenting Ghosts in the Air Traffic. It's a talk about protocols in air traffic controller, mainly new protocols which are being deployed now. A little bit about myself. I used to write some my fair classic key recoveries, some PostScript and printer hacking, and recently a little bit of interest in avionics. But generally, I'm a PhD in embedded security and some kind of symbolic execution interest. So, if you are into the topic, you can check with me or chat. So a small disclaimer because it's related to airplanes and kind of sensitive critical infrastructure stuff. Don't try this at home, or even if you try, I mean, it's good to experiment, but make sure you just do not transmit on the antenna. Just put a cable, use attenuator. Just make sure make due diligence not to transmit actually in the air because it's quite important, and we don't want to lose important hackers doing jail time, right? Uh, okay, so this is a short agenda. How we'll be going. We'll present shortly what is ATC looking like today, what problems does it have today, how it is supposed to be looking tomorrow or in the nearest future, meaning the ADSB, the protocol which we'll be addressing. What are the problems in the new protocol? What were not the lessons learned? And basically some of the scenarios and demos in detail and some solutions and takeaways. How many of you are more or less familiar with air traffic controlling, have done some sniffing on ACARS messages? Just one, two? Yeah? Okay, so I hope you find it interesting, and I'll try to, if it's very technical, just raise your hand, I'll try to adapt. Okay, so how ATC means air traffic controllers, and how it looks today. Basically, it's a very complex system because mainly it's based on legacy stuff, and the most complex part in this system is the human. Why? Because it's error prone, and there were some cases, even in Switzerland, sadly, there's a long some history regarding some air traffic controller situation with some Russian flight, which is not very funny story. So the weak link are the people involved in all the air traffic controllers, and it's actually a very complex system, complex job. It involves a lot of risk, a lot of stress, and basically to eliminate the human cost and the human factor, which is the highest complexity and higher error rate, and it cannot be controlled. Basically, the idea is to move from human-centric to computer-centric air traffic control, which surprisingly, maybe it will surprise you, but now it's human-centric, meaning that all the computers are mainly aiding people to make decisions and make inputs to the pilots and to the other systems. It's not computer-centric where a computer decides and human is just correcting the action of the computer. Okay, so ADSB is the new protocol which is being built on top of the existing infrastructure, which is supposed to basically automate some of the tasks of locating precisely the air traffic in the air and knowing where it moves, how far away are the planes from each other. But now, before ADSB, they had to rely on something else, which is called basically primary radars. Sorry? Yeah, primary surveillance radars and secondary surveillance radars. So primary surveillance radars are very expensive military kind of stuff. They cover a big region, and they use the electromagnetic waves bouncing. So basically, it's the big rotor antenna, which you usually see in some very important hubs, which send electromagnetic waves If it's a big object in the air, it gets a bounce back. It knows it's something in there. Okay, it knows something in there, but it doesn't know a lot of information. Is it a plane or is it something else? If it's a plane, what information is there? So on more regional scale or more local scale, they have the secondary surveillance radars, which basically, after identifying that somewhere in the space is the object, they send interrogation asking what are you, who are you, and what are your parameters, like in general terms. So in the first step is the transmittal signal. It carries basically no higher level information if we somehow want to relate to OC model, and just a signal and a signal back. And then it's the transmitted interrogation where you have actually some frames, some modulation, some packets, and some information going back and forth between the ATC rotating antenna and the presumable aircraft. So basically, in order for this to work, the existing systems before ADS-B mandate that all the aircraft have a device called transponder or XPDR. You'll find it XPDR or transponder. Basically, it's a transmitter and responder. It's an abbreviation. It has a lot of external antennas and some cockpit control panel where all the data coming and going out from the transponder is being displayed to the pilot, so the pilot can make more or less informed decisions or replies to the ATC or surrounding aircraft. Some of the data which is being carried by the transponder is the aircraft address. Aircraft address is a 24-bit ICAO unique identifier. ICAO is the International Civil Airline Organizations, Aviation Organizations. And basically, you can think it as a hardware MAC, right? Where every airline or country has a prefix assigned, and then within every prefix, they have sequential numbers assigned to each aircraft. So basically, it's a MAC address kind of a thing, but assigned to the aircraft, 24 bits. Our information, because, okay, the primary surveillance radar and secondary can locate an airplane on let's say, horizontal axis. It cannot very precisely locate with this thing its altitude. So basically, the idea is, and altitude is quite critical in maneuvering and especially in landing. So the aircraft has to reply with the altitude, which it takes from barometric sensors. GPS is not that reliable in altitude, so there's a lot of other kind of sensors which they try to get the most correct altitude. Okay, so this is in general terms how it is working still now and how it worked for the last 50 or so years. And basically the system is working, but it has its own limitations or problems. So the idea is that if you go through all the specs, it's like huge specs, different kind of subsystems involved in aircraft or in parts of the network of ATC. You find all these kinds of instructions in manuals. So basically the pilots have all kind of transponder. They can put some kind of flight ID settings when they do a specific flight, like flight AF1234, Air France 1234. So they can set some settings which goes over the air to the ATC. So the manual says, like, don't add any leading zeros, hyphens, dashes, or spaces to the flight ID, or ATC might not be able to see your aircraft or might confuse it with another. So clearly there's something wrong in the system where the inputs are not robust enough, where a small error in the inputs can generate an ITC not being able to see an aircraft, right? It's like the same kind of thing which you try to say a user or developer, do not put a quota in your name, even though your name is O'Reilly, right? I mean, the other things is, again, user controllable or pilot controllable inputs where they can set specific like status codes. Like you can see these squawk codes or status codes as HTTP codes, like 200, 301, 302, 404, and so on. So for various types of situations, they put these squawk codes on the transponder, which is being squawked to the ATC. And some of them the user can control, the pilot can control them, and they can put it to, if indicate by mistake or on bad purpose, hijacking, or they can put it to indicate like military interception, and they like allow you to put this code, but say never ever put this code. And it happens by mistake or under stress. You can actually make these mistakes because the dials are octal systems. So you can basically, if you see the highlight up is like, if you want to go from code 2700 to code 7200, you have to switch first the second dial, the first dial. So you go through 2200 and then 7200. Otherwise, if you switch the other dial first, you squawk the emergency, right? Which is crazy by itself. I mean, it's like, and imagine this is a scenario where the pilot has a situation in the aircraft, or he is also communicating with 10 aircrafts. He's getting input from ATC. He's also has to know which dial to dial first. I mean, this sounds crazy. I mean, shouldn't work this way. Okay, so we said, okay, there's a lot of human error and potential error, like from human side, from everywhere, pilots, ATC, and so on and so on. So they said, okay, let's do ADSB, which is automatic dependable surveillance. Basically, it's automatic, more or less, no human interaction. Dependable because it depends on GPS or GLONASS or Galileo. Surveillance, it's, again, because you want to know where the system is. And the funny thing is the B at the end, which means broadcast. So if there's any crypto guy in the room, when you hear broadcast, usually it involves, not very simple stuff. If you want to do crypto and broadcast, there's a lot of problems. So we'll get down to it later. So ADSB is like a multi-billion worldwide effort from 2002. They started it in 2002. And it's just very interesting for management people because I know usually there are some management or CTOs or CISOs in the room. It's like billions of dollars spent on this project in the US alone. It's not yet fully implemented. And the funny thing is that we'll go down to the security of it, and you'll see where these billions went. Okay, some of you already see. So how does ADSB work compared to the classical non-ADSB? The classical non-ADSB, sorry, I forgot to mention, it's called Mode S, or extended squitter. So basically, we have a lot of definitions. Some of them are confusing, some of them overlapping. So it just it's Mode S. In ADSB, you have, again, the aircrafts, and you have the ground station. Basically, it's the same kind of ATC tower, but without a rotating antenna. It's just a pole with a specifically tuned antenna. And it has connection to ATC. The ATC can be geographically located in our country because there's regional ATCs which manage like an area of air traffic surrounding multiple countries. And what this antenna does is basically it sends and receives data from aircrafts. And the data is, again, a structured data. It can be 112 bits or 56 bits. The 56 bits carries the old format kind of data, and the 112 bits carry the new format. It's simplified view. So, and also you can have the communication between the airplanes. So basically, airplane exchange messages between them, saying I'm this airplane, I'm at this position, so take care not to have a collision. And they basically derive the exact GPS location, or basically more generically global GNSS, okay, which can be particular GPS, GLONASS, or Galileo implementation. Okay, so as you can see, here's two things mentioned. So basically, ADSB out means that the aircrafts, they send information, ADSB information outside to the other entities, and ADSB in, which is a newer feature which is not yet implemented, but is being pioneered in Europe by Swiss Airlines. So ADS-B-in is a feature where actually the aircrafts receive information from other aircrafts or ground stations and basically process this information in the form of displaying it on the display or making different kind of decisions like avoid collision and so on. So ADS-B is interesting because of several reasons. One of them is that compared to ATC, where it has internet connectivity and it can check whether an airplane exists or not, an airplane app doesn't have full-time or connectivity at all, so it cannot reliably verify. It just has to trust that data, right? When it comes in, it has to trust. It doesn't have all the means as an ITC to verify a specific data. So bad data is maybe worse than no data at all. So it depends. Just a little bit of a breakdown. So in Mode S, basically the existing and old kind of technology, there's Mode S and Mode AC, basically which transmit aircraft address, altitude. Then there's enhanced mode, which basically transmits some more parameters, which are more technical parameters. Okay, then on top of the same kind of technology or on the same kind of infrastructure, they said, okay, let's build ADS-B out, which is basically broadcasting also the position, which was not there. Basically, the position was derived based on quadrature and basically signal, and they derive the sector and get the altitude and somehow approximate where the aircraft is, and then they also get by voice confirmation from a pilot that yes, I'm at this position approximately. So they include the position derivation and the position broadcast in the ADS-B technology, and they add the velocity, direction like azimuth, bearing, and flight ID. Okay, and then they just extend the standard with many more features. And basically, at the end, the goal is also to implement ADS-B-in, where they have real-time like information about all the aircrafts around any other aircraft, right? So the pilot have full awareness and somehow magically can act without ATC help. It helps usually in areas above oceans where there is no ATC infrastructure, so easy accessible, so they have somehow to rely on. There are some problems which they have to work out. So just to wrap up a little bit on the architecture side, ADS-B is basically a protocol built on top of existing infrastructure, and it basically works over Mode S infrastructure, which is basically interrogation goes on frequency 1030 megahertz. So basically, an airplane or a base station can interrogate other airplane by sending an interrogation on 1030 megahertz, and everybody else replies or broadcasts on 1090 megahertz. It uses PPM, pulse position modulation, at 1 megabit per second. So basically, 1 bit is 1 second, microsecond, sorry. And newer technology, a little bit newer, is universal access transceiver, which is basically a frequency shifting keying at 1.1 megabits per second. And it works on 978 megahertz, but this technology is a little bit newer. It's not there on all aircrafts, and it's not there on all ground station, so it's not very popular. Most of the people, I mean, normally an aircraft or a company which invested a lot of money in aircrafts, it will not change the technology overnight, like shifting from 1090 megahertz to better 978 megahertz, because it costs a lot of money. So they'll be just sticking as maximum as possible on the technology they invested their money in. Okay, this is a very high-level overview of the next gen, what they call in US. In other countries, in Europe or in Australia, they call it differently. So basically, it's kind of a holistic vision of the future E-enabled aircraft communication and transportation system. So there's a lot of subsystems. Basically, we cover
the broadcast data link ADSB between aircrafts and ground, and broadcast inter-aircraft data link, meaning ADSB between airplanes. And there's a lot of other protocols. So if you are interested in this stuff, there's a lot of protocols to go and play and research. The specs are not so freely available, but you can still find them. Just to see how much progress have we done in ADSB deployment. So there's Australia, which is basically almost 100%. I think by the mid 2013 it will be 100% coverage. So basically, any way over Australia, they can know which airplane it is and what is the flight ID, and also basically all the or most of the aircrafts flying to Australia will be required to have this kind of technology on the airplanes. In USA, there's a little bit different pattern. It mainly covers the busy ports. Here's the desert, the rest of the world. Okay, so these are kind of data. So these are ground stations, and they belong to to government or to the national space agencies or whatever not. So how the community, like me and you and everybody in this room, gets this data? So of course there are some open source and there's also some commercial receivers which you can basically go and buy in form of these boxes, which come with forum, professional customer support, hotline, software upgrades, but they also cost like 500, 300 euros, which is a lot of money for a box which does a simple thing like receiving simple modulation, demodulating, and showing it on Google Earth, right? There's smaller and less expensive variants, and some people just try to build their own stuff on very simple device. So you can see there is a big box which, okay, has a lot of networking and so on, but this one is like 20 euros, and it does exactly the same thing. You just need to write the software, which is mostly available as free FOSS. So all the people around the world, they gather this data, and they aggregate it on online sites or on applications for your smartphone, which show you basically in real time. Okay, they show with a delay of 5 minutes to deter terrorist attacks, but I mean, if you are interested in specific regions, just go with the device there and you know in real time where the plane is, right? So you can see that there's a lot of traffic going on, especially in Europe. So, and here I think are at most 2,000, 3,000 planes displayed on a small area, and you can see how cluttered it is. And it shows a lot of presence of ADSB technology in Europe. And yeah, there's somebody showing this online, I think. So, I mean, there's a lot of sites because it attracts a lot of people because it's a cool stuff to see. Here's this airplane. I can see where's my mom is because she's flying in or flying out. So some of them even add features to attract more users, like show virtual display. Basically, they take Google Earth 3D plugin. They take the position. They take the kind of view from a given altitude and show what the pilot sees or what the mom sees from the window of the aircraft. Okay, so I mean, you can imagine how far you can go. Basically, you can run 3D simulators for any kind of a plane. Just take all the panorama and show. So, okay, so this is kind of usage side of the technology. Now we'll go a little bit on the more technical stuff, like ADSB frame. As I mentioned, it's structured data. It comes in frames. It uses pulse position modulations. So basically, pulse position modulation means that depending where the pulse starts, it's either 0 or 1. So basically, for 0, it's low to high, and for 1 is high to low. So you can see, again, 0 is low to high, 1 is high to low, again, high to low. So it's easy, right? I mean, no complex stuff. One of these bit is 1 microsecond. So basically, you have 1 megabit per second bandwidth. What it means? It means that in one given second, there can be 8,000 or 9,000 frames being transmitted. And because it's a broadcast and there is no collision avoidance or collision detection in the protocol, you can see that if there is more of 9,000 aircrafts transmitting on the same kind of area, which is, okay, not a standard situation, but nevertheless, you can see that all the messages will be jammed exponentially. So, like after 3,000 planes transmitting at the same time to a given tower, the messages will jam themselves. Will be like because no CA, no CD, and yeah. Next is the format. So basically, it's the data link kind of level. Now more on a frame level. Basically, there's a preamble, which is it's not standard PPM. Basically, it's a preamble with pulses, 4 pulses at specific timings, and they are used to synchronize the transmitter with the receiver. So basically, the receiver knows that what comes next is most probably an ADS-B frame. So please sync with me, and then from this point onward, try to decode it as PPM. Again, yeah, so this thing is 8 bits. Okay, we call it bits, but it just lasts 8 microseconds. So you know that if you find in a given time frame 8 microseconds with this pattern in the form of IQ data coming to your FPGA or whatever your radio is, you know that most probably you'll have a frame. Then it comes the data block, the whole data block, which can be 56 or 112 bits. So it ends up as 8 bytes or 15 bytes, right? So 8 or 15 bytes long, the entire thing. And mandatory of these are the ICAO address, which is 24-bit and basically 6 hex digits, and 24-bit parity for error detection and they say correction. So, but correction mostly works on UAT 978 megahertz. In Mode S, it doesn't work. I mean, it's not supposed to work because it's like very simple one. The parity again is not a secure hash. It's just used for error detection. It's not used to make sure that the message is genuine. It's not a signature. Again, I mean, it takes 10 years or more to explain to some developers that parity or error code is not a security feature. I mean, it's sometimes it's just hard to believe that people do not understand the difference between error code correction and the hashing mechanism. What is the difference? So most of the people think this is enough to validate the frame that it is okay. Yes, it's okay, but you don't know where it comes from. And on the security, we have, I think, this says it all. So if you go down to the specification PDF, which is quite big, no word about security. They have safety, they have a lot of this marketing bullshit, but on security, no. So safety and security is a little bit different. Okay, so as you can see, because there is no security and there is no hashing, there is only just integrity check, you know that the frame is good. But there is no security on the protocol or on the frame. You can see that there's a lot of problems. So just a quick rundown of the problems, like entity or message authentication. You don't know whether message is authentic, means you don't know whether it was generated by a true aircraft, by a prank hacker, or by an UFO. It can be generated by anything on Earth. Entity, again, you don't know the message, again, you don't know whether it's, you know only that it's valid. It's according to specification and the error check is fine, but you don't know who generated it. Second is kind of a derivation, and it's put as a warning. Entity authorization. I mean, usually to be able to transmit on these frequencies, you need license and you need devices. And those devices you can buy only if you are an airline company or airline supporting company. You cannot just walk in, give 100,000 and say, I want one of these boxes. So basically, by the legislation and by the way the things work in this network, it's like entity authorization is enforced by the regulation itself. But at the same time, because the medium is shared and there is no security on the medium, you cannot actually enforce entity authorization like forcibly, right? You cannot put filters of radio frequency and say, oh, you're not authorized. I mean, the authorization model is a little bit also broken. It's not related, it's kind of related to technical aspects, but it's also broken in the regulatory sense. Also, there is, as you could see, the ICAO address, basically the unique identification is in clear text. And you know, everything which identify an entity in clear text is like equal, not equal privacy. So you know which airplane is there, and if you think that it's not interesting to know the identifier of a particular Swiss Airlines airplane, think about identifier of Air Force One. I mean, if you know that's an Air Force One, suddenly it becomes a very interesting target, right? So these identifiers are unique and they're like hardcoded. I'm not saying that Air Force One is broadcasting its real identifier. I don't know how it works actually for Air Force One and this kind of targets. But again, if they fake it, then what's the whole purpose of unique identifier if somebody fakes? Like, you know, as you can change the MAC address on Linux. There is no message integrity. So basically, besides message authentication, you don't have message integrity where the entity sending it, you cannot be sure that the message, even though sent by a real entity, authorized entity, you cannot be sure that the message was not altered in the way to its destination. So its integrity is not being assured because there is no security message authentication code, HMAC. Okay? Again, there is no message freshness, meaning there is no nonce. You can take a valid thing or generate your own valid message and replay it continuously. Just keep sending, keep sending, keep sending. And the idea is that if it pops up on the AirTraffic controller screen, he doesn't know, I mean, maybe it's a helicopter which is stuck, but maybe you don't know why the same flying stuff is on the same position because you keep replaying the same message, sending I'm at position X and Y and Z, right? So there is no message freshness which would ensure that there is no replay attack. Okay, obviously there is no encryption because encryption in highly mobile and broadcast environments is hard, is not an easy problem. But it doesn't mean you don't have to address it, especially when the technology is based on tens of billions, not millions, billions of dollars, right? I mean, when you invest such amount of money, you can hire the best brains in the world to address at least part of the problems. And surprisingly, in auto industry, they get it, that customers will not buy the cars if there's no enough privacy and security features. And they actually build these kind of privacy preserving protocols on VANETs, which is vehicular ad hoc networks, right? Where there's a lot of cars and they are very ad hoc networks. They combine in networks on very ad hoc basis. So basically they address these security issues in vehicular systems, but the parallel is very similar with aircraft, but they do not address it, even though they have much more budget than the automobile industry. And last but not least is the fact that there's massive public databases with details of both corporations and both individuals owning particular aircraft. So basically you can know individuals, their name, their address in most of the countries or most international associated countries who owns an aircraft. So it's like, imagine that you could go in any country. I'm not sure how it works in Switzerland, but you could go to any country online and check whose car is this. You just enter the registration number. It says everything about the owner. It's a privacy breach, right? So apparently it's not the case in, as I show later, it's not the case for this. technology. Apparently, there exists what they called ADS-B crypto-secured version. But apparently, it's used in military. They call it Mode 4, Mode 5 IFF, Identify Friend or Foe Crypto Applique. And is defined in this standard. And you can see that's a military standard. And basically, mostly they use it for military planes. And according to the brochures and the very limited information, so if anybody has, please leak. Basically, they rely on black and red keys crypto type. So it's a little bit of a problem because if it's military and governments are involved, the leakage of red keys involve the conspiration of all the black keys, and basically the model is broken. So because there is no mutual trust in the whole system, they just cannot start and giving black keys and red keys to everybody, and just it's a mess. But they could find some kind of a compromise solution. Some of the quick. Okay, I have 15 more minutes, 10 minutes. Okay, I'll go. So we have the adversary model, which the adversary can be anybody, anywhere. By anybody meaning it can be the pilots themselves, if by bad intent or by stress or by some other means. They can be pranksters. Basically, think pranksters as one-click script kiddies, which I'll go at the end of the slide, and you'll see that it's a very potential scenario in the future for one-click script kiddies for hardware stuff. So they can be abusive users or criminals, or okay, imagine what can military intelligence do. An example of pilots, intentional or bad intent, or I don't know. Basically, they used to set these flight IDs like ATC fail, big boobs, bad sex, you suck, high dead, going for home and get a job. So basically, they use this kind of system to transmit to each other messages over, okay, the protocol is public, so they're amateurs listening to these frequencies, they dump all these funny things, they put them on a forum. If you look, it's not very hard on the Google, I don't give a link, but you can find it pretty quick. Okay, external abusers and public data correlation. So basically, you're in Cannes, there's a festival, you know there's some star coming, you have a sniffer, you have the database, you correlate, you know, okay, now this guy is coming, we'll take some photos, okay? Because usually they do not say who is coming, so the idea is to find out before all the other crowds. And you'll be surprised that a lot of, okay, in US, they give you like 39 megabytes zipped CSV files, which unpacks to 300 megabytes or something like this. So they have all kinds of expiration date. They have street, city. Okay, this specific example, which I looked up online, is FAA, but you can find the individuals, private individuals, phone numbers, and so on and so on. They have it for Australia. They give you like 15,000 records, downloaded CSV, just import, correlate. You saw the first talk, CSV, Facebook, graphs, and you're done. Just draw nice planes, put online. And the most funny thing, I like the UK-style entrepreneurship, where they actually offer you for 1,000 British pounds, they offer you databases of 45 countries with over 400,000 aircrafts on a DVD-ROM. Okay, they call it CD-ROM. Maybe it's a CD-ROM because, yeah. So just go and click on forms and fees. If you get a copy, please share or leak. Okay, so by location, very quick. Basically, ground-based means you stay in your basement, you stay in your van, you hook up your power amplifier, you hook up your receiver or transmitter, which is worse, and you start sending messages because there is no crypto and everything is software-based nowadays. You can program it, you can send. The problem with ground-based, you can get quickly triangulated, trilaterate, whatever you call it, and we are pretty strict with it, and you get code very quickly. However, with new technologies, think about putting this kind of stuff on home drones and UAVs. Okay, you triangulate, trilaterate, try to catch that. Not quite easy. And all kinds of various scenarios where you can put everything with a lot of batteries in Pelican case, check in your luggage, and go. Okay, there's some potential on DOS attack, as I explained earlier. If you remember the slide with a lot of airplanes, like online application, right? Flight Radar 24, where you saw that like after 1,000 airplanes, the screen is so cluttered that you cannot understand anything, like, right? You remember that slide with a lot of airplanes. So basically the same thing an attacker can do, just he has 1 megabit, he can send basically 9,000 of fake airplanes in 1 second, right? So every second he generates another 9,000, and usually the airplanes which appear on the screen, they do not disappear exactly at the moment there is no signal. They stay persistent for a while. So if you do it like for 60 seconds, you get like 500,000. I don't know. So maybe in 1 minute there is a refresh on the screen and some of them go away, fade away because there is no signal from them. So basically there's, even though the bandwidth is limited, with enough persistence you can put a lot of them like on the screen, and the screen is unusable, right? I mean, you cannot figure out anything. You will think that the system is bugged. Or you can just fake the same plane, you put the same ICAO address, but it puts you in very different locations. So the screen is like moving like hell, right? I mean, it's crazy because it's not secured in the first place. Okay, of course, if there's other attackers or other airplanes, number of messages you can inject decreases because of a collision, but nevertheless, if with enough persistence, you can do. So what's required? In our experiment, we used USRP1. You can use any USRP. This is what we got. It was cheapest. You have 2 options for transmitting because both of these are transceivers. Price is not different. A little bit the sensitivity and basically the frequency range is different. But you can we've done with SBX, but you can do the same with WBX. You might want to use the BSRX2 for kind of receiving back to your USRP and validate that the data you fake is really according to the specs. We also used, and it's a good idea to use some commercial, like third-party small device to see that your messages are being received by not only your system, but other systems as well. And yeah, don't forget cables, attenuators. Do not put this on antenna, please, 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 please. Okay. The slides will be available. I don't go into much details because it's not workshop, but it's a good reference point if you want to start hacking into this. All these Python scripts, most of them are in GNU Radio. Okay, the missing part is the encoder. You have the decoder basically to receive, but to encode, you need to write some code. But as you saw, the modulation is like pretty straightforward. If you stay at night, very persistently in C++ or Python, you can write it. Okay, because I have a little bit of time. Some fun facts is, for example, you can do ADSB fuzzing. I'm not sure how many vendors do this or how many air traffic towers do this. For example, in our case, for the little box, it comes with a software, and with fuzzing found that it doesn't show the planes which have ICAO address starting with 0. I don't know, maybe it's a software bug, but the same kind of software bug can exist in real traffic screens. I don't know. So, okay, I'll just do a very quick demo. I'm sorry I don't carry the equipment with me because it's sensitive. You are on a flight. It's like a very bad combination to carry this stuff. It's not because that it will trigger itself, but the problem is that they start asking questions and we say, okay, we know what you are doing and you have this equipment, so would you follow us, please? Or no. Okay, so what we have here is this plane plotter. Maybe some of you are familiar with this. It's kind of free, not free, but it's very used software where you get input from various boxes, which I showed earlier, like commercial and open source ones. You get the data from them, and this software basically decodes the input and shows on the plane. So from the USRP, we send the cable input to the commercial little box, okay, and the little box sends the data to this screen. Basically, we start our script, and you can see that it's already receiving our signals. These are two signals, which are for two valid airplanes we captured, and then we replay. Okay. The setup is clear, right? So we replay some captured data, which we capture from some valid planes. Now, watch out for this. We, for example, aim for simulating a collision on the traffic controller. Watch this one, because see, we moved it back a little bit because we want for collision to happen on the screen. So did you see the jump? Okay, so basically we moved it a little bit back, and then just by natural course of things, the system on the ATC might say, you have a potential collision, please take action. Where actually there is no collision and there is no plane at all, right? Because we replay it. So, okay, it goes on, it shows that it has a potential to replay, to modify some messages in real time, to modify the perceived position of a fake plane or a real plane, and you can see that it can generate some panic in the room. Which is not good, because, I mean, the technology is so insecure, it shouldn't be like this. And at the end, we also do some, okay, you can see there is, you cannot distinguish, but there was like 3 airplanes here, 3 airplanes, and 3 airplanes here, right? So imagine if I start putting like 300, 300, you start distinguishing nothing. And as you can see, we can send also to traffic controllers messages like, I'm not sure you can see, it's like dead, ADSB, fail, cafe, babe, boobs. So basically we encode this hex speak in form of ICAO addresses, but I mean, you see, right? The dead, the AD5B, which is ADSB, fail, cafe, babe, and so on. So basically you can do a lot of stuff with it. Okay, very quick. No, it's a very good reference. I'll just show you briefly why is this important, because I'm sure there's maybe 1, 2, 3, maybe 10 managers in this room. The time scale is important. I have done a timeline on ADSB. Why I want quickly to show it, I want to show that it's important to assess the technology ahead, especially when the Moore's law is like proven like for so many years. When you build a technology, you don't look only now, you should look ahead. So when they started building the specification for ADSB, they started as grants to some research universities. They started doing researches where they come with theoretical solutions. What they didn't know is that, and then they happily announced that after doing the research and doing the specification, they say, okay, we'll implement this sometime in the future. What they were not looking as managers and decision makers is that in less than 1 year, the USRP will appear, right? And you could know that in 2001 and 2002 by following GNU Radio community, because it was very active on developing this. So if you build a technology which is radio-based, and you know that somebody is building a software-defined radio box, you might want to think about this, right? I mean, when you start building a multi-billion project. Okay, but they ignore. So basically what happens is they just ignore. And as you can see, basically they publish happily the specifications. These are the specifications. Okay. Then they start working very hard. There is like quiet on both community and on the specification part. And basically, the funny thing that in 2007, they say, okay, finally we almost deployed and we start basically testing, and immediately, like in a couple of weeks or months, on GNU Radio, there's somebody written, because the system already live on US, right? They wrote this kind of decoder. So you have to look very much ahead. And what's coming up is, okay, the takeaways from this. The good thing is with this kind of research is that they, like in 1-2 weeks, they are meeting to create a cybersecurity task force because of this kind of research and the presentation we've done at Black Hat. So kind of the good takeaway, that they somehow take note, take action, and try to do something at least. So kind of a win, a good. The bad thing is that still ADSB is safety-related mission-critical technology, and it lacks minimal security, and I don't know how they will fix it, because it's based on old infrastructure, and they didn't take into consideration many assumptions about how technology will evolve and how the people will start using this technology. And some of them start asking, so should we ban software-defined radios? Because apparently they are bad, right? No, fix ADSB, not SDR. SDR is good, it moves technology forward. But the ugly thing is that, like recent developments, like you can get a sniffer for $25, which is RTL SDR, if you don't take a look. And the another ugly thing is you actually get a pocket-sized USRP for $300. It's basically the early days price of Proxmark 3. And this is the size of a Proxmark or a little bit more. It goes to 2 gigahertz. So imagine guys running around, and all this runs open source software, GNU Radio. Imagine guys running around or sitting around you or sitting on a plane with this kind of one-click solutions. Well, you have to account for this when you develop a technology. So that's a very important. Like from $2,000 to $300, there'll be at least 7 times more, if not, buyers to use this technology, and then and so on. Lot of references and links, and I would like to thank my professor Aurelian and Euricon for the time on this research. And thank you. If you have any questions, sorry guys, the time is up. Please catch me in the lobby. Yeah, thank you very much.